Hi, this is a Keithley DMM 7510. It's a pretty schmick 7.5 digit multimeter, one of the best you can get. So if we can have a look at what it can measure in terms of low current, well, on its lowest range here, our decimal point is here on the microamps range. Move the decimal place 3 spots over, and that's nanoamps. Move it 3 spots over again, and that's picoamps. So it basically has 1 picoamp resolution. Pretty schmick. But this is amateur hour. This is what you want when you're measuring low currents. 35-year-old technology, the Keithley 617 programmable electrometer from the early 1980s. This is a fantastic bit of kit. Not only can it measure voltage, it can measure ohms. Thank you very much. Gigohms, hundreds of gigohms. If you want to go that high, it can measure coulombs for those playing along at home. Everyone loves coulombs. And it can measure current. How low can it go? Well, how high can it go? Well, look at this. Milliamps. No worries. Microamps. No worries. Keep going. Keep going. Nanoamps. That's for amateurs. Picoamps. That's for amateurs too. Let's have a look. Its lowest range is a 2 picoamp range. And that's picoamps. That's puff. So there's our decimal point. If you move, you can't really, black point is hopeless, isn't it? Move the decimal place 3 places over. That digit there is femtoamps. This one here is 100 attoamps. Atto. Most people don't even learn what atto is in engineering. It's like, what prefix is that? 100 attoamps resolution. Now, pretty much, there's only a couple of instruments that can, like mainstream instruments that I'm aware of that can beat this. These days, there are a couple of modern ones that can go down to 10 attoamps resolution. But this one can do 100 attoamps. Absolutely amazing. 35-year-old bit of technology. For those playing along at home, that is 62.5 electrons per second. For 100 attoamps. Whoa, this is heavy. So what do you need something like this for? Well, basic physics and material research, new nanotube research, new polymers, and various other, real low current electrochemical type applications where you're pretty much down to the level of counting electrons. It's ridiculous. Anyway, 100 attoamps resolution, and please excuse me for turning it on before I take it apart, but I just had to show you that how low this thing could actually go. And we can, this is the actual, I've got nothing plugged into it at the moment, and we can actually there we go. I had it on 0 there, but there we go. It's actually counting. If you fart on the other side of the room, this thing's going to change by like 100 counts. So clenching my butt cheeks. I better not breathe either. Anyway, look, we can 0 check that, and it's got an internal internal 1 femtoamp offset there, and we can 0 correct that before we take our measurement. Unbelievable. Now, it's actually got a voltage source output as well. Voltage generator, 103 volts maximum. Very nice for powering stuff under test. It allows a higher resistance mode as well using the built-in voltage source. And also it's got some monitor outputs as well. So you can actually, we'll have a closer look at the schematic up there, but it's got the obligatory IEEE 4008 GPIB interface. And it's also got outputs which tell you that the completion of the measurement has done, and external trigger as well. So you can trigger it and then it gives a response when it's taken that measurement. So good for system integration. So you can see that you can actually get a preamp output here and also an amplified analog output as well. And that might be handy for, once again, system integration stuff. Now, of course, you can't just use a regular BNC or banana jack inputs for this sort of thing. You've got to use a special low-noise triaxial connector, it's called. It's called triaxial because it looks like a regular BNC, which is basically a biaxial. And this has actually got a third contact in there. That gold one around there, if you can see that. closely. So don't just go plug in a regular BNC cable into a triaxial connector. You'll bugger it up. So this actually provides a separate internal shield in there, as different from internal guard, different from the external output here, and that's critical for really low noise measurements. But you'll also find them on very high resistance meters as well. One's designed, once again, they're ultra low current, but 1,000 very high voltage system. High resistance meters, for example, will actually use these triaxial connectors for testing at 1,000 volts. And, you can pay $1,000 for a test cable that comes with this instrument. But considering that one of these modern instruments is $7,000 for the base model unit and $15,000 for the for the top of the range model, then, people are used to paying $1,000 for a special low noise triaxial cable. Manufactured by nude virgins. Now, unfortunately, I don't have a triaxial connector here in the lab handily. I'll have to order one so that I can, do some better experiments. So I'll just plug some sharp probes up its clacker and see if it's bang on. Let's have a look. Here we go. Tongue at the right angle. Oh, look at that. Bang on to the least significant digit. Awesome. So I'm not going to go to the effort at the moment to measure all the other ranges. That requires specialised setups to do. But suffice it to say that if it's bang on the 1 milliamp range, odds of it being good on the other ranges are high. Confidence is high.
Confidence is high. I repeat, confidence is high.
And check it out, the built-in voltage generator, it works as well. So let's set it to 5 volts, shall we? There you go. It's only a smidgen out, but this can actually go up to, as I said, 100 odd volts. It actually will have an adjustable velocity thing, so should get there reasonably quick. Ta-da! There it is. 100.45. Not bad at all. So basic functionality seems to be there. Awesome. And I love gear that has the instructions on the top. Look at that. Beautiful. Why can't they do that these days? Anyway, let's do a teardown of this puppy and enter the world of attoamps. This is going to be interesting. So what we're going to see inside here is, I'm guessing, this isn't just going to be running via the coax just across the cable over to the PCB. It's going to be going into a nice big shielded block or something like that. There's 2 screws on the back. The rest of it's, of course, all going to be regular stuff. There's just going to be some magic on the front end. And, whoop, yep, we're in like Flynn. And, ta-da, there it is. There's our magic block. That's where all the magic's going to happen. And look at the external power supply over here. That's hilarious. In fact, that transformer, that's bent. That is not camera angle. That's not my eye going wonky. That transformer is... This thing's... Can I just bend it back? Jeez. Check out down in the mains input down here. Look at this. It's right near these signal outputs. Look, not a single toss was given about making it, aesthetically, physically separate from the rest of it. But, as long as you got your clearance on the PCB, it's all hunky-dory. So what they're doing is running the mains traces down here. There's a little common mode choke there, running them right down the edge of the board, right past all the active circuitry. Once again, if the clearance is there, okay, but, it's not exactly modern design technique. And then they've got the mains, real clunking, mains power switch on the front there. Not sure what that puppy's doing there. It's not labelled. I have to read the manual on that one. Anyway, so we've got our mains input and then our line fuses next to that. Oh, and the Motorola 6805 fanboys go wild. There it is, in socketed. Thank you very much. And then we've got the obligatory SRAM next to that. Well, I can't read that. What is that? Is that? Yeah, 6116. Of course it is. Absolute classic. And then we've just got our basic ROM. So, of course, 6805 processor and the TMS 9914 up here. This is actually the GPIB interface chip, and you can't half tell because it's plugged into all the micro on the bus, and then they all bugger off up here. Got some drivers, and then it goes over to the GPIB connector. Sorry, IEEE 488. So we've got our date code there, 85, there it is, and yeah, some of the other chips down there, 85. I'm not going to, who cares about all the digital stuff? Not me. I want to see what's inside the can. And we've got some AC coupling to the chassis, of course, for system noise reasons. Just a couple on there. Look at the braid they've got in there. By the way, little pro tip, when you're using your solder wick, don't throw away your used solder wick. Actually, keep them in your offcuts from those. Keep them in your parts drawer. They're very useful for really low impedance straps like this one. It probably doesn't need the low impedance. Somebody's put the strap in there, but yeah, they can be useful. Keep them. Oh no, some of the glue is starting to peel off there. Look at that. That's it. They've got a shield all the way. The entire box is shielded, as you'd expect on an instrument of this class. And it looks like the board in here, it's all going to be, through-hole stuff just like this. But it looks like they got it on the one board with the power supply over here. This is, of course, a dedicated analog power supply for this analog section. The other transformer down here has got its own stuff for all the digital thing. It makes sense to separate those. But yeah, it looks like they've got it all on the one board and calibrated by 1065. Good on you, 1065. And inspected by 1300. Some of the unsung heroes of Keithley. Wonder where they are now. All right, let's reveal the magic here. A couple of little trimmer holes up there. You've got to trim those at the right angle. You're not allowed to probe through there unless you've got your tongue at the right angle and you've got a grey beard. So let's... Ta-da! Oh! Check it out. Whoa, I got some jazzy stuff going on here with this can. We'll take a closer look. But of course, what you expect to find in one of these things is exactly what we see. Standoffs here. There is too much leakage on PCBs for this sort of stuff to be going into PCBs. So we've got ridiculously low leakage relays here. We'll have to check those out. Might see if I can't even get a brand. ET? Phone home. Anyway, what you expect. PCBs have too much leakage. They get crap, contaminants, oil, dust, condensation, all sorts of crap on them. So you want point-to-point wiring on this sort of stuff. Teflon standoffs, maybe they're not Teflon because Teflon can actually build up a static charge. That can be a trap for young players. But yeah, you can see our input is going directly over here, over to the standoff there, into these relays, which are doing the range switching. And have you ever seen a 250 gigohm, not megaohm, gigohm resistor before? Well, you have now. That's the input impedance of this thing by the looks of it. Now, on a quick search, I didn't find anything for these relays here, but I'll have a better look if I can. I'll include it, but these are going to be ridiculously low leakage, hermetically sealed relays. Now, I've actually done a video on talking about one of the designs I did back in the day for a company I worked at, where it was once again, measuring high resistances and at high voltages, and we required a relay matrix like a massive relay matrix, hundreds and hundreds of relays, and all the problems involved in actually designing one of those things. It's one of my very old videos from like 7-8 years ago. I'll link it in down below and at the end of this video. Check it out. And whatever that little metal can there is, it's very important because they didn't want the metal can just flapping around in the breeze, so they had to actually have a strap tying that down to some sort of guard point. It's probably not going to be ground, it's going to be a guard point. There is a difference between ground and guard point. I might have to do a separate video on that because that's kind of an interesting topic in its own right. Now, you might be able to notice down in there, or maybe not, might be a bit hard, but all the magic, of course, is happening in our dual matched FET pair here. And you can see that one of the leads just in there, bugger going to the PCB, way too much leakage and whatnot. So it goes, they've bent it out at right angles like that directly to the standoff. So you can see that the signal path comes in here from the coax, and then it goes through the various relays and then goes to, various input impedances and stuff like that to get the current, of course, because we're measuring current. We've got to put it through a resistor, measure the voltage across it, basically. So we've got the fixed, and here's the fixed 250 gig resistor here. So that'd be used for the 2 picoamp range there, and that is directly on that node there. So everything travels above the boards, like, you know, Manhattan style, above the boards, Manhattan construction technique, which is a technique of dead bugging components on copper-clad board and then just point-to-point wiring. Might include a photo if there is one. And yeah, so it all stays off the PCB and goes directly into our dual matched FET there, which of course is going to be a super duper special matched characterized one manufactured by nude virgins with grey beards. See if we can get the part number on that. It's got a 168 and then an 852A on there. And T-TG on the front of that and an M. It's not, doesn't look like the Motorola job. Anyway, if I can pull up any data on that part, I doubt it. Like, you know, this could be a Keithley internal part number. You may not know what that dual FET input is. Anyway, if you blow the arse out of that, yeah, good luck getting a new one. So all you young whippersnappers out there are probably going, what's the big deal? Like, it's got some relays and a dual FET input and bloody fancy-pantsy triaxial connector, but whoop-de-doo. Well, go try and design something like this. Go try, design it, test it, and then get, you know, a proper controlled characteristics in production environment, and you'll find out very quickly how difficult this is to get right. It's not rocket science, it's electron science. And you'll notice that the grounds are going all over the shop. Not only did the shield here for this matched FET bugger off to somewhere else over here to some guard ground, but, well, some guard terminal doesn't have to be ground, but the shielding for this case up here, which is isolated from, well, supposed to be, it's touch in there, isn't it? Did that cause an issue? Like that, eventually touching there, cause an issue? It may do. I don't know. Anyway, like this ground is buggering off somewhere else. The shield for this is buggering off somewhere else. The triaxial, I presume that green wire in there is going into the triaxial shield guard inside there. So it's buggering off downstairs somewhere, which we don't know about. And just getting all this stuff right is not easy. Anyway, got ourselves a CADAC hybrid resistor network there, so that's pretty nice. But apart from that, you know, we've got like the 250 gig resistors. They're not going to be cheap. 100 meg, 100. I think we've got 100 gig. We've got 100 gig, a 250 gig resistor, and there's a 100 meg one in there, and various other. Yep, there it is. There's your 100 meg one. There you go, for the different ranges. They're going down in decades, of course, to give you your different ranges. They're the shunt resistors, just like on a microcurrent, for example, except it uses a fancy-pantsy FET front end and really high-value resistors. It's simply the voltage drop across a resistor. But, yeah, the relays are super-duper special. If we get down in there, haven't fully removed the board yet, but check out, yeah, the triaxial guard is coming from that point down there, as is the shield for the can. So it looks like, as are two different wires buggering off there, buggering off somewhere else on the board, we've got ourselves a star ground-in point there. So it's all referenced back to that one point. So they certainly know what they're doing. And here's the circuitry underneath there. So that's actually all to do with like the 100 volt high voltage power supply over here. And take a look at this and notice something interesting. Look at this big strap over here, this big crimp connector. There's from the 100 volt output over here. They've got that going through what looks like, you know, a massive high current lead. It's not doing that. It's going over to this capacitor here, which then couples into the ground, and that ground is on the output, which straps into, which has an optional strap to the earth ground, which then straps optionally into the output ground over here. And of course, whether or not you include that ground guard strap there is all to do with your system implementation and how you do that. So you have to really know what you're doing when you're playing around, you know, implementing this sort of stuff and taking serious measurements, not in terms of using the instrument, but your system setup, and all your system grounding and things like that. It's really important. And looks like those extra system ground wires that star ground in, I told you about, is going over here. Looks like one of them's going into the main ribbon cable, which then goes back up to the main connector at the top, the main analog input board at the top. And thankfully, we have full access to the schematics for this thing and all the theory of operation, the whole works. I'll link in the manual down below. The regular manual has all this stuff in it. It's not just the service manual that you used to be able to get. It's all in the main manual. Fantastic. They don't make them like this anymore. Anyway, take a look at the notes that they've got for just assembling this PCB. Look, Freon clean the PCB, flow and touch up using rosin flux, wash immediately after the flow. In Freon, solder the polystyrene capacitors. Polystyrene, thumbs up, love polystyrene. They're super stable capacitors used for, high precision circuits like this one. After the Freon, you've got to do that after the Freon wash, and then remove flux locally with Freon, and then clean thoroughly with methanol after flow and touch up in dashed areas. What? Components mounted on Teflon, so they are actually Teflon standoffs. That's interesting. So static mustn't be a problem. Keithley know what they're doing. And must not touch PC board or other components because, they have to be completely isolated. So there you go. It's just like assembly steps. That's just great. And we have the schematic for the AD converter as well. No, they've rolled their own analog to digital converter. It's a constant frequency charge balance single slope job. And well, it's got theory of operation in the manual if you want to go into that. But yeah, they've basically rolled their own. It's not like they just bought an analog devices ADC. Nah, bugger that. And of course, this is what everyone wants to see, the front end. How do they do this? How do they get like Atto, 100 attoamps, femtoamp levels on this thing? Well, let's take a look. The input, as you can see that the guard there, the 3 inputs, and the guard, as I said, goes down to mates down to the motherboard, so it goes around in various configurations for that star ground and all that. And you can actually see that there are different symbols used for the different grounds there. And look over on the right-hand side near K301, over there, that relay, you can see that that's actually a star ground point, and that might go back to the main board that we actually saw back down the bottom, that star ground point down on the bottom PCB. So as we've seen in the teardown, it doesn't go to the PCB at this point. It's all off-the-board construction. That input signal goes to those rows of standoffs and those relays that we actually saw there with the, it's just up in free air. So it's not touching the board, so it's completely isolated, air-gapped isolated from everything. Goes into those special squirrel relays, which I still can't find any data on those, but they'd be ridiculously low leakage. And you can see that if you go through R334, 355 and 332 there, then you can see the 250 gig ohm resistor permanently going down to ground. So that's like 250 gig ohms is that permanent input resistance there. And then the other ones up the top there, right at the very top, there's the 100 gig R330 there, and then 331 100 meg. Then they'll go down in decades, 100K, and so forth for the various ranges. Now, of course, this isn't, those don't go down to ground. They're part of the feedback loop, part of the feedback amplifier. And of course, if you look at the theory of operation, this is actually a feedback amplifier. So the shunt resistor in quote marks, the resistor that the current needs to flow through, convert it to voltage, is in the feedback loop of the op-amp. And the op-amp here, you can see it there, U309, is actually a Linear Technology LT1012. And that's a pretty schmick op-amp, but it's only picoamp level input, right? So it's not good enough picoamps. That's amateur hour. So they use Q308, the dual match JFET input, as the high impedance input required to get the attoamp level. So this is a very special matched transistor, probably hand selected, hand tested, hand graded, everything else. And I looked in the manual, the parts list for it, and they don't actually give a part number. So, it's super special secret squirrel stuff. Presumably, if anyone does know, please tell us down below. Anyway, that is what gives you your extremely ridiculously high input impedance. The only thing that can do the job here is JFETs. None of this MOSFET rubbish, like really special matched JFETs there for the front end. But apart from that, that's where all the magic happens, and physically as well, where the magic happens. It's all off the board, choosing these components like the matched JFET, like the relays, mounting them off the board, but everything else is just pretty much off the shelf. The LT1012 and U304 up the top there, whatever that is. They got a 6.3 volt voltage reference Zener, and like the rest of it's pretty ordinary stuff, really. So yeah, all the special stuff: transistor, relay, Manhattan construction. That's the ticket, laddie. So there you have it. I hope you enjoyed that. Interesting looking inside the Keithley 617 electrometer. And these things, they're still available for all sorts of physics and materials research and all sorts of weird and wonderful stuff. Don't have much use in your regular electronics, of course. They might be used in semiconductor, fabs and other places for various things. But, your general purpose electronic lab is not going to need to go down to attoamps like this thing can, or even femtoamps, really. So, you might go picoamps, nanoamps is quite common for low power stuff, but, even picoamps is like usually several orders of magnitude beyond what your regular electronics person ever needs to deal with. But these things are very specialized bits of kit. They have their place. That's why they're so expensive, having the matched FET front end and all the special relays and everything else, and they don't manufacture these in high volume, which is why that they can charge $7, $8, $10, $15,000 for these sorts of things. They are precision bits of kit. Lots of engineering goes into them, but you might look at it and go, meh, whatever. But try and do it. I dare you. Try and measure, hundreds of gigohms, teraohms, and femtoamps and attoamps. It's just crazy different world. Anyway, if you liked it, please give it a big thumbs up. As always, there are high-res teardown photos on EEVblog.com, linked in down below. If you want to discuss it, comments, all that sort of stuff, link to the EEVblog forum. Hope you liked it. Catch you next time.